Hi folks, today Simran and I are going to present our work describing how simple linear attention models balance a trade-off between recall and throughput. We're currently experiencing a Cambrian explosion of new efficient language model architectures that rival transformers. Seems like every week there's a new efficient language model architecture popping up, accompanied by a compulsory animal mascot generated by DALL-E. Taken all together, these works paint a pretty clear picture. There exists a class of efficient language model architectures that are far faster and cheaper to run than transformers, and importantly, that seem to generate text that's just as high quality as the text generated by a transformer. And yet, despite all these really promising results, the organizations trained the largest and strongest language models are sticking with the transformer architecture for now. But in some sense, it makes sense that folks are reluctant to make the leap away from transformers. By no free lunch, we know that when we get something great, like way faster training and inference, we must be giving something up. Prior works don't tell us what that is. So it's actually reasonable that folks are waiting to dig in until they know the price of the meal. In this work, we wanted to find out what exactly we're trading off when we move to these much faster architectures. Going one step further, we also try to characterize this as a smooth trade-off space controlled by a property or hyperparameter of the architecture. And finally, we're going to develop new architectures that are at the Pareto frontier of this trade-off space. I'll briefly outline the rest of the talk. So first, I'm going to provide some background on the building blocks of large language models and explain why these efficient architectures are so fast. Next, I'll answer the question posed in the previous slide, showing that there is a sizable gap in performance on a class of tasks that we'll refer to as recall-intensive tasks. Afterwards, Simran's going to demonstrate a fundamental trade-off between a model's efficiency and its ability to perform those recall-intensive tasks. And finally, she'll show how we can navigate the Pareto frontier of this trade-off space using simple techniques. All right, let's start by providing some background on these architectures. To do so, we need to discuss the basic building block from which most of today's language models are built. So the transformer block transforms a text representation using two operations, attention followed by an MLP. This one building block is repeated dozens of times inside of the model, and it accounts for basically all of its computational cost. So if we can make this one little building block more efficient, then the whole architecture should run much faster. As I mentioned, there are tons of new efficient architecture proposals like Mamba, GLA, RWKV. And all of them are specifically focused on replacing the attention operation with something more efficient. So what's wrong with attention? Why does everyone want to replace it? The main issue is that GPU memory consumption grows linearly with the length of the text when using attention. All of this memory consumption limits the throughput of the model because one, it reduces the batch size that you can use, and two, it also increases the traffic on bandwidth connecting the GPU memory to cores. So all of this memory consumption goes towards this construct called the KV cache. In the interest of time, I'm going to brush over why the KV cache is necessary to generate with intention. But you can think of the KV cache as the model's working memory during generation. So when a user types in a prompt, like, can you recite Moby Dick? That prompt text will be stored in the KV cache. Each token in the text is going to be represented by a d-dimensional key and value embedding. Then once the model starts generating, every token that's generated is also going to be added, and the KV cache is going to grow to accommodate it. Once the model is done generating, we'll have consumed memory proportional to the length of the text. So the main reason these new architectures are so much faster than attention is that they consume constant amount of GPU memory, independent of sequence length. This enables larger batch sizes and less communication on the GPU, and can lead up to like 24x higher throughput over attention. So to understand why, let's consider linear attention, which is a very simple, efficient alternative to regular attention that's closely related to some of the most exciting architectures today, like Mamba. In linear attention, all we do is drop the softmax from the attention computation. This allows us, by the associative property, to multiply the keys and the values first. Now, we don't need to maintain all of the key and value vectors separately now. Instead, we can collapse them into a single compressed state of size d squared. So our KV cache is now replaced with this new memory object called the KV state, and its size is independent of the sequence length. So now when we generate, we store tokens by summing them into that KV cache matrix, and we don't need to increase the amount of memory that we consume. So with this additional background, we can make our research question from earlier a bit more precise. We're asking, what do we lose exactly when we get rid of the KV cache and replace it with something of constant size? Cool. So the first question to ask after hearing that a new efficient attention alternative is as good as attention is, what data sets were the models evaluated on? We found that most works were evaluating on the standard suite of language modeling tasks that include things like Lambda, HelloSwag, and Arc. And indeed, when we went ahead and evaluated different models on these tasks, we found that they all matched or came very close to matching the performance of attention. But if you look closely at all these tasks, you'll see that they're composed primarily of short questions over short contexts. It was really surprising to us that these architectures were so focused on these tasks, given that the long context is the motivation for a lot of these efficient architectures. For example, this question from Arc is only a few dozen tokens long, and it's still pretty representative of all the data sets in this standard suite of tasks. But the difference between these models lies in the size of its working memory, and the questions are really short, so it's unsurprising that they perform just as well. Instead, we're going to consider a new set of tasks that stretch the limits of the model's working memory. We put together a small suite of what we call recall-intensive tasks, which are tasks where the model needs to recall information seen in context in order to succeed. In the long document question answering, the model is presented with a long passage of text, like a Wikipedia article, and then asked a natural language question about it at the end. In information extraction, the model is given a dense unstructured document and it has to extract a set of fields like a JSON object from it. When we evaluated the models on these tasks, we found that efficient alternatives like Mamba or H3 performed worse than attention and by very, very large margins. Convolution-based models like H3 trailed attention by 40 accuracy points, and more recent linear attention-like models like Mamba trailed by around 30. And this was still operating at 2048 context length, so the issue could only exacerbate when we go to 32,000 tokens or 1 million tokens and beyond. These results really shocked us. We suspected that there might be some task where the efficient models might perform worse, but we didn't know how big the gap would be. Given the importance of processing long context in LLM applications, it had become quite clear to us at this point that understanding this gap was important. So in what follows, Simran's going to demonstrate that there's a fundamental trade-off at play that relates the size of a model's working memory and its ability to perform recall.
Thanks, Sabri. Sabri showed that the strongest efficient architectures really struggle to perform recall. I'll demonstrate why and then show our solution, a new architecture called BASED, which makes progress in closing the gaps to attention. So to study the recall problem, many works have taken the real task and abstracted it into synthetic tests. For instance, in the test on the right, the model is given a context of key value token pairs. C maps to 8, A maps to 3, and so on. The model then needs to use this information seen in context to answer queries on the right-hand side. What was very surprising to us in the course of this work was that prior work had actually shown that efficient models like H3, Hyena, and Mamba were perfect on synthetic recall tests. Obviously, this contradicted the downstream results that Sabri showed, so what gives? We really need a precise formalization of the problem if we want to explain what's going on with associative recall. You can check out our prior ICLR 2024 work to learn more, but we discovered key issues in the prior formalizations and fixed them with our new improved formalization called MQAR, supported by theory and experiments. We show that model quality on MQAR actually correlates with the downstream trends that Sabri showed. We've been very excited to see MQAR become the de facto recall test and help people design new architectures like the ones shown here on the slide. In this work, we trained a broad range of models on the MQAR synthetic and used this to explain the gaps that Sabri showed. We plot the total inference state size on the x-axis and the associative recall accuracy as a measure of quality on the y-axis. First, we find attention solves MQAR perfectly, but has a large state size from the KV cache. Next, sliding window attention, where each query attends to a fixed number of prior key and value tokens, reduces the memory consumption, but drastically drops off in recall quality. Excitingly, Mamba expanded the Pareto frontier over sliding window attention by using a selective state space modeling approach. We also find that popular gated state space models like H3, Hyena, and RWKV fell below the Pareto frontier. We theoretically explain this in our work by providing a lower bound on the number of layers of gated SSMs versus attention required to solve MQAR. So if you're interested in this, I encourage you to check that out. Across these architectures, we see clear trade-offs between the memory or recurrent state size and the quality, or MQAR accuracy. To formalize this trade-off, we can think of inputs as streams of tokens. We show that the MQAR situation is related to the classical streaming setting, which has been studied for decades. While keys and values are streaming by, we have to remember the value for an arbitrary key. It's not so hard to see that this requires at least omega n of space for n keys. The natural question is, can we expand the Pareto frontier of the memory quality trade-off space? Given the large gaps we've been seeing between our strongest subquadratic models and attention on the downstream tasks. We observe in our work that linear attention can help us traverse the trade-off space in principled ways and use this to design a new architecture that helps bridge the gap. So let's dive in. Recall from the beginning of this talk that linear attention replaces the exponential of QK transpose in attention with 5Q times 5K transpose for some feature map phi. Unlike sliding window attention, linear attention will provide a global approximation of attention along the sequence dimension. It uses input-dependent sequence mixing like standard attention, and it also retains subquadratic training and O1 constant inference in sequence length n. Our work specifically makes use of a Taylor approximation of the softmax exponential function as our linear attention feature map. Recall that x of x can be written as 1 plus x squared over 2 factorial ... to infinity. The Taylor exp is a really exciting feature map in several respects. 1, simplicity. It's a very direct natural approximation of the softmax exponential function. 2, conceptually, we can directly traverse the quality efficiency trade-off space by toggling the fidelity of our approximation. So infinite terms exactly represents x, but requires infinite dimensions in the computation, so would be efficiency-wise infeasible. We choose to use a second-order approximation, which offers nice quality. However, the second-order term still results in a drastically larger recurrent state size compared to prior recurrent architectures. For comparison, the state size is 8 times larger than that used in the Mamba architecture per layer. So this means we really need to critically consider a custom CUDA implementation to make our architecture competitive. We provide novel algorithms in our work that implement the Taylor linear attention using GPU tensor cores. This is particularly notable since our baseline subquadratic models, like Mamba, cannot take advantage of tensor cores. So even though our state size is large, we can still be efficient. Of course, since we don't have a perfect exp in our linear attention with this approximation, it won't exactly match attention. But we can combine linear attention with a dense sliding window attention to get the best of both worlds. Taylor gives a global attention approximation, and sliding window gives a precise local attention. This idea of combining local and global sequence mixers is very fundamental, and you can read more discussion in our paper. Very excitingly, BASED expands the Pareto frontier beyond the other subquadratic models on associative recall, for instance, the Mamba architecture shown here in yellow. And these results extend to the downstream tasks, where BASED closes a large portion of the quality gap between Mamba and attention on recall. At the same time, BASED provides 24 times faster generation compared to flash attention and 50% faster inference prefill. We're very excited about these results and their impact on pushing forward subquadratic models. For instance, the Mamba 2 architecture that was released just last month also switched from using SSMs to linear attention with larger state sizes, following the based approach. We developed our custom CUDA algorithms using a DSL called Thunderkittens, and you can play with it at the link shown here. Think of Thunderkittens as the equivalent of like PyTorch to ML architecture development. We tried to provide clean, simple abstractions to make CUDA development a lot simpler. Altogether, we hope that this work helped develop your understanding of how to compare the many different efficient architectures. There's no free lunch, and there's a fundamental memory and quality trade-off. Check out our posters and come chat with us to learn more. Here's the amazing team of collaborators that made this work possible. And thank you for watching.